to 460 euro per cubic centimeters, while batteries are ranging between 0.0007 up to 1.6 euro per cubic centimeter, depending on the battery you are using. The high value are for lithium batteries, the low values are for the alkaline. Under these conditions, it's much easier to work with the batteries instead of the energy harvesters, because they have a 4 orders lower cost per volume ratio than energy harvesters. Nevertheless, if we are considering the parameters of different batteries, then we can find at least a very interesting behavior. We have a self-discharge rate of batteries. And this self-discharge of batteries is relatively high. It's not low, it's high. So if you are going to use a battery, you have to look for the self-discharge, and it ranges in percents per month. As you can see, for an alkaline battery, it's about 3% per month. For a lithium, it's about in a range between 1 and 8. It depends on, is it a lithium or a lithium-ion battery. This leads to a bad situation for the batteries, because if you have a battery and you want to use it and you store it for, let's say, some years, then it's empty. So you can't use it anymore. So you have to replace batteries. So we can say batteries are typically sufficient for many sensor applications. Modern lithium batteries show a very high energy density. The operational lifetime counts in years, and they are relatively cheap. But they have a self-discharge, and furthermore, a permanent discharge or high discharge currents require the replacement of batteries. So you can use batteries, or you have to exchange it, especially by energy harvesters. So what are the basic reasons to use energy harvesters? One is replacement of batteries. So we are looking for that, and we have developed the following criteria. As first, if the areas are not accessible. So if there is no replacement possible, it's better to work with an energy harvester instead of a battery. Or if you have a demand on a permanent constant power supply, then it's better to work with an energy harvester. Or if you have the situation that you want to work simultaneously with a sensor and an energy supply as well, then it's better to work with an energy harvester. Or in some cases, you can work with one power energy harvester and one power adjustment unit. Or finally, in some cases, the use of power grids or batteries are not really wanted, and in that case, you don't work with an energy, you can work with an energy harvester. So I will come to some samples which we are doing, or which we have developed, energy harvesters, which can be used in water pipes. In water pipes, that means we have a built-in curing installation, so it's very hard to come onto the sensor or onto the electronic during the lifespan of the whole device. And they normally measure flow rate, they measure temperature, pH value, and some people want to measure some biological information. Everything is possible. And the problem is they don't want to have wires to the outside because of the leakage of these devices. So if we are looking to our criteria, then we can say the application criteria 1 is completely fulfilled. So we have developed a simple device. And the simple device is looking like that. It's a piezoelectric conversion we have a type of a pipe, and in the pipe we have something like a plug body. The plug body will generate some turbulences. These turbulences will force a PVDF. PVDF is a material which is piezoelectric, will force a PVDF spool to oscillate, and the PVDF spool is directly connected with a flexible board with sensors, power management, and all the other things which are needed. So we come to the PVDF spool, which is interesting, and the spool we are using is a PVDF spool consisting of 2 layers of PVDF and in between 2 layers of aluminum to omit a breakthrough between the 2 layers, as you can see over here. This is omitted, having this construction. Under these conditions, we have made the first experiment, as you can see over here. We make the first experiments in an airflow, and you can see here the energy harvester. This is the type of the pipe, and the airflow starts and the energy harvester operates. It moves up and down permanently, and it delivers a certain amount of voltage. And the voltage, can you see over there? It's a typical sinus shaped voltage with an output which is not really high, but it's enough to feed something like electronics. But this is in an airflow. If we are considering that, then we have impedance matching, or we have a power adjustment, and the power adjustment has been achieved at an impedance of about, what can I say, 3 mega ohm, and the average power is about 0.45 microwatts, which is not really very much, and the power density is 2 microwatts per cubic centimeter. This is due to the situation that PVDF has a low conversion efficiency in comparison to, let's say, PZT. Nevertheless, we did the same experiment also in water. This is a little bit more heavy because water is not a really good material for experiments. And you can see the fluttering of the device, and this is the electricity we have achieved from the water experiment. You can see it once again. It's fluttering a little bit different to that of air, but it works very well as well. And having water, we have, in that case, a power in a range of 0.6 microwatt, and this is the power what we have achieved at the power at a load, as you can see here, of about roughly 2.5 megawatts. A second example is sensors on the floor. And this is a built-in during installation. They are typically not accessible during lifespan, and they can measure mechanical loading. They can use to make counting, occupation, triggering of light switches, and something like that. And they have no wires to the outside because of security reasons and others. So we have the situation that we have no accessibility, and we are using the energy harvester as sensor as well. The problem is, if we are looking to applications for in-floor harvesters, typically you have a man sitting in a room and the light is switching off due to no movement. If you have a typical movement sensor, then you can move and the light switches on. So the man makes some movements, the light switches on. But in some cases, you don't have the movement and you don't have the movement sensors. Consider sometimes if you are going into a toilet, you go into the door, go into the next door, and there is no sensor inside. And then you have the situation, no movement will work. Our idea was to have a sensor in the floor, and applying a step on the floor, then you can generate something of energy and the light switches on. This is very interesting for a lot of applications, especially for persons who are going onto the toilet during the night. If they are step on the ground, they can switch on the light only by their footstep. The problem is, we want to work with a PVDF spool as basic element, because it's a very cheap design of an energy harvester. A PVDF spool is extremely cheap. It's a polymer, just wound to a spool, and it costs not very much. Generation of strain in thin polymeric films, having a spool like that is difficult. So